Deep in the constellation Ophiuchus, 760 million light-years from Earth, a black hole is misbehaving. It isn't just devouring matter, it's echoing like a drum, pulsing with energy in patterns no one expected. Its gravity twists space in ways that break the rules. According to Einstein, this shouldn't be happening. And yet, here it is, observed, recorded, verified. What if everything we knew about gravity was wrong? What if this one enigmatic object, dark, silent, and ancient, held the key to a deeper law of the universe, one that could overturn a century of physics and redefine our place in the cosmos? Join us as we unravel the strange case of a black hole that defies Einstein and explore the mind-bending possibilities that might lie beyond the edge of known science. At first, it looked like a data error, a flicker, a wobble, a strange pattern in the background noise from the able 2261 Clusterer region of space, already infamous for harboring a galaxy with a mysteriously missing black hole. But this wasn't the absence of a black hole. It was the presence of something wrong. It started with a team at the Event Horizon Telescope, cross-referencing updated polarization data from their 2023 observations. They were hunting for subtle shifts in magnetic fields near black holes, tiny clues that might refine existing gravitational models. Instead, they found a beat, a rhythm, a pulse so steady it seemed orchestrated, almost artificial. Every 9.8 hours, a low-frequency gravitational drumbeat echoed through their sensors. Not a signal from matter orbiting the black hole. Not jets. Not noise. Something else. At first, the team thought it must be instrumentation interference, solar activity, anything more mundane than what the pattern implied. But then came confirmation. Data from the Chandra X-ray Observatory taken years earlier showed the same rhythmic fluctuations, as did radio data from ALMA, when reanalyzed under a new lens. Across wavelengths, across instruments, across time, the pulse was there. Dr. Renata Soto, a senior astrophysicist at Caltech, described the moment her simulations failed to model the behavior. It was like watching the laws of physics skip a beat, she later wrote in her research log. We ran the equations again and again. None of them predicted this. None of them allowed this. And that was the problem. Black holes, under Einstein's general relativity, are governed by incredibly precise rules. Their spin, mass, and charge define them completely. They do not pulse like hearts. They do not echo like bells. They certainly do not repeat themselves like clocks ticking through time. And yet here was one, doing all of that and more. This wasn't random. The signals had harmonic structure like a musical note modulating over time. If black holes were supposed to be cosmic endpoints, why did this one sound like a beginning? The black hole in question, designated A2261BH1, wasn't just large. It was monstrous. Over 10 billion times the mass of our Sun. It resided in the heart of a galaxy cluster where cosmic collisions had once torn entire galactic cores apart. Some had even speculated it had been ejected from its galaxy due to gravitational recoiler theory never proven. But now, it had made its presence known, and it wasn't just there, it was talking. The team scrambled to understand what the pulses could mean. Could they be remnants of a past event? Shockwaves from a merger? Or were they something far more fundamental, fluctuations in the very fabric of spacetime? NASA issued a quiet internal memo flagging the anomaly for further review. Papers were written, but not submitted. Careers were quietly realigned. Because If this black hole was violating the rules, then so was everything built upon those rules. It was a scientific whisperer, prelude to a scream. There's a haunting irony here. For over a century, we've treated Einstein's equations as gospel. Black holes were their most extreme, most beautiful consequence. But now, this very creation, a perfect child of general relativity, was misbehaving. It was like finding a symphony that plays itself backwards and still sounds beautiful. Familiar, but wrong. And that was the moment the shift began. Researchers from MIT to Max Planck began poring over the datasets. Algorithms were rewritten. Theoretical physicists dusted off long-abandoned models. And slowly, a terrifying, exhilarating idea began to take shape. What if this black hole wasn't defying physics, but revealing deeper ones? What if the pulsars weren't an error but a message? Imagine staring into a cosmic chasm so deep it devours time, and hearing it whisper back. Now pause for a moment. Think about the sheer impossibility of that. What would you do if a black hole started speaking in rhythm? Would you listen? Would you believe? At some point, science is not just about data, it's about confronting the edge of belief. And in 2023, that edge was found in the darkness between galaxies. And so began the search for answers, for patterns, for the flaw in Einstein's frame. Because if this pulse is reality, it is then something in the universe has changed. Or perhaps, something has always been there, waiting for us to notice, waiting in the silence, waiting in the pulse, waiting in the dark. For over 100 years, general relativity has been the bedrock of modern physics, triumph of human intellect, carved from the mind of a man who saw time not as a constant, but as a river bending to mass. Einstein's 1915 theory rewrote the cosmos. Gravity wasn't a force, but the curvature of space-time itself. Planets moved the way marbles roll across a stretched rubber sheet. Light bent around stars. Time ticked slower near black holes. And it worked. From Mercury's orbit to GPS satellites, from gravitational lensing to the image of a black hole's shadow itself, general relativity has stood, unflinching, perfect, impossibly elegant, until now. Because the black hole, in Abel 2260, regular, impossible, has done what thousands of experiments never could. It found the edge of Einstein's frame, a boundary, a place where the rubber sheet wrinkles and frays, where equations lose meaning, where certainty begins to bleed. But this isn't a new idea. Not really. For decades, physicists have whispered about the limits of relativity. The theory collapses under its own weight at the heart of singularities, how it refuses to coexist peacefully with the quantum world. The chaotic dance of particles and probability that governs everything else. Relativity is classical, deterministic. Quantum mechanics is not. At the Planck scale, the universe's deepest foundation, they fight like oil and water. Both true, both irreconcilable. But until now, those contradictions were hidden, veiled inside black holes, too distant and too violent to test. Like secrets, locked behind cosmic iron doors, until this one opened and pulsed. Let's rewind. Einstein's equations predict that a black hole's event horizon is smooth, silent, and absolute. Nothing escapes. No signal, no memory. A black hole has no hair. As the saying goes, no unique features beyond mass, charge, and spin. All information is erased, lost. But quantum theory screams in protest. Information, it insists, cannot be destroyed. The universe keeps a ledger, Somewhere, somehow, the data must remain. This clash between quantum law and Einstein's gravity has been the greatest unresolved paradox in all of science. The information paradox. Hawking tried to resolve it. So did Penrose. String theorists joined the fray. Loop quantum gravity offered alternatives. But still, no consensus. No breakthrough until the pulse. Because if a black hole can remember if it leaves behind regular, structured signals, it means information is not lost. Something remains. Something leaks through, and that changes everything. To grasp the implications, imagine you're standing on a beach, watching waves lap against the shore. For a century, we believed black holes were like sinkholes, swallowing all memory, leaving a still, dark pool. But now, ripples are returning. Patterns emerge in the tide. The ocean is not silent, so physicists begin to wonder, are we finally glimpsing the bridge between Einstein's world and the quantum realm? Enter Dr. Eshin Malik, a theoretical physicist at the University of Tokyo for years. He's been working on a controversial framework called quantum geometrodynamics. According to him, the universe at its core is a fabric woven not just of space and time, but of relationships. In his models, gravity itself arises from entangled networks of information, changing the very nature of what a black hole is. When shown the able 2261 pulse data, Dr. Malik didn't laugh. He didn't dismiss it. He stared at the waveforms and said quietly, "It's begun." Because for Malik, this was the missing piece. Not an anomaly, but confirmation. He believes the pulse is not a glitch in gravity, but a signature, the boundary where general relativity hands the baton to a deeper law. Like Newtonian physics giving way to Einstein, Malik believes we are witnessing a shift in paradigms, a peeling back of the sky. But if that's true, why now? Why this black hole? Some suggest that what we're seeing isn't unique, but universal, that all black holes may pulse, may echo, may harbor memory. We've just lacked the tools, or the curiosity, to notice. Others argue it's the environment table 20-61's unique gravitational history, the ancient collisions that shook it into chaos. Perhaps the black hole absorbed more than just matter. Perhaps it's metabolizing time itself. Still, others warn, maybe we shouldn't be so eager to understand it. Maybe this is like dissecting a thunderstorm. Beautiful, yes, but dangerous. And that raises a question we must all ask. What do we do when the laws that governed our sky, our lives, our understanding of the cosmos suddenly seem incomplete? Do we hold tighter to the known, or let go and fall forward? For some scientists, this is liberation. For others, it is dread, a shattering of the sacred. Einstein gave us a universe of predictability, but now we stand on the edge of a new wilderness. And this is only the beginning, because if relativity is not wrong, but incomplete, then what comes next? Something stranger, something deeper, a new equation, a new map of reality, a theory that might finally unify the two halves of existence, gravity and quantum mechanics, space and information, order and chaos. But to find it, we'll need to follow the pulses, even if they lead us into the unknown. At the heart of galaxy cluster Abell 2261 lies a gravitational monster, one of the most massive black holes ever suspected. Estimated at over 10 billion times the mass of our Sun, it should be, by all accounts, an active cosmic furnace, a roaring engine surrounded by a seething accretion disk, blazing jets of high-energy particles, radiating X-rays like a lighthouse in deep space. But this one is quiet. Too quiet. No violent flares. No thermal signatures of matter spiraling inward. Just darkness and pulse. Like a cosmic heart that beats but doesn't breathe. The silence was deafening to Dr. Akash Mehta, a high-energy astrophysicist working with archival Chandra X-ray observatory data. In 2024, while reviewing emissions from Able 2261, Mehta stumbled upon something bizarre. The emissions didn't match the predicted age or behavior of the black hole's surrounding environment. More astonishingly, the rhythmic pulses didn't originate from any known material process. They were imprinted across time. Something's wrong, Mehta whispered to himself as he aligned the datasets. These pulses are older than the galaxy's current active phase, older by nearly 400 million years. That realization struck like a thunderclap. The black hole was pulsing now, but the same pulses could be traced to a time before the current galactic core had restructured. It was as if the black hole remembered a past galaxy, as if it carried echoes from an older universe. This shouldn't be possible in standard cosmological models. Black holes don't keep time. They don't record history. Their gravitational fields are absolute. They swallow causality. Memory, as we understand it, doesn't survive the event horizon. But here was a black hole that didn't forget. Let's pause on that dot. Imagine standing before a creature so ancient it has consumed entire stars, and yet it still hums the rhythm of a cosmic age long dead. What would that mean? What would it say about the universe's deepest layers? Some began to call it the ghost core, a reference to Able 2261's unusual galactic center, which appears bloated and diffuse. In 2012, astronomers noticed that the central black hole had seemingly vanished. It wasn't where it should have been. Now, over a decade later, it hasn't just returned, it's left behind a trail of gravitational fingerprints. And those fingerprints don't just tell a story, they rewrite one. In examining the radiation signature of a 2261 BH1, Dr. Mehta noticed subtle interference patterns embedded within the pulse cycle. These weren't just time signals. They resembled something far more exotic, phase-locked harmonics, a pattern often found in self-regulating systems like biological rhythms or computational processes. Could it be that the black hole wasn't merely pulsing, it was processing? The implications rattled the astrophysical community. If the pulses were computational, then what was being computed? Was this the residue of quantum memory, or something else entirely, a structure beyond classical spacetime, a remnant of a previous state of the universe? The debate reached fever pitch at a closed-door symposium in Geneva, where theorists and observers gathered to cross-examine the anomaly. Some speculated that the black hole was part of a collapsed binary system, a rare pairing of supermassive entities, whose interactions left behind gravitational scars. Others proposed a bolder theory, that this wasn't a singular object at all, but a hybrid part black hole, part exotic structure, perhaps a gravitational solitone, or even a stable wormhole residue. What unified all the perspectives was a single, unsettling truth. A2261b did not behave like any black hole on record. And that brings us to a painful reckoning in science, a moment when nature shrugs off our categories. We tend to think of black holes as known quantities, despite their mystery. We classify them by mass, spin, charge. We simulate them. We trust them. But what happens when one doesn't play by the rules? What happens when it sings instead of screams? This moment echoes across scientific history. We thought atoms were indivisible till they weren't. We thought Newton's laws governed everything until Einstein showed us space bends. And now we may have thought black holes were the end of physics, but perhaps they're only the beginning. Maybe black holes aren't endpoints. Maybe they're archives, memory vaults of the cosmos. And maybe, just maybe, a 2 to 6 1BH1 is a lullaby from a universe long past. So ask yourself, if this black hole can reach across cosmic ages, what else might lie encoded in the darkness? And if we're only now beginning to hear the pulse, how many others have we missed? As Meta noted in his final report, either we've found a black hole that shouldn't exist, or we've found the first real evidence that they're far more than we imagined. Either way, we're on the edge of something vast, something we're only beginning to understand. In Cape Town, at the edge of the African continent where the Atlantic collides with the sky, a different kind of collision was happening between theoretical physics and something even more elusive. Imagination. Dr. Lynn Okoro stood before a digital rendering of the Abell 2261 black hole, her brow furrowed. She wasn't an astrophysicist by training. She came from the realm of field theory and higher dimensional mathematics, places where most physicists hesitate to go without a flashlight. But when she saw the rhythmic pulses in the Abell data, something clicked. It wasn't just gravity behaving oddly, it was something extra. Something outside the familiar for forces that hold our universe together. Gravity, electromagnetism, the strong force, the weak force, and now, possibly, a fifth. For decades, hints of a fifth fundamental force have danced just beyond the reach of confirmation. A blip in particle behavior here, an unexplained asymmetry there, but nothing stuck, nothing decisive, until now. Dr. Okoro proposed a radical hypothesis. The black hole's pulses weren't merely distortions of spacetime. They were echoes, reverberations from an interaction with a fifth force, one not bound by the traditional architecture of reality. Her theory rested on something called gravitational solitons, self-sustaining wave packets in curved space. Think of a ripple in a pond that travels endlessly, never dispersing. In classical physics, solitons are rare and exquisite, but in warped space-time, they become something more profound. Single quotes, as simulations showed that if this fifth force existed, an interdimensional field that couples weakly with gravity under extreme mass density, it could create standing waveforms around black holes. These waves would resonate, repeat, pulse, like a bell struck gently, in another dimension. And here's where it becomes almost poetic. These solitonic echoes wouldn't just be distortions, they'd be music, space-time singing in harmony with a hidden force, a chorus we've been deaf to until now. But what's the instrument to answer that? Okoro turned to string theory's lesser-known cousin, brain cosmology. In this framework, our universe is a 4D membrane floating in a higher dimensional bulk. Gravity, uniquely, can leak into these extra dimensions. The other forces cannot. So if this fifth force was real, it might be born not in our universe, but in the space between universes and black holes. They could be where the membranes touch. Think of them not as holes, but as contact points, interfaces, places where our world kisses the unknown. When Okoro presented her early findings at the International Conference on Gravitational Frontiers, the reaction was a blend of awe and skepticism. Some dismissed it as mathematical fantasy. Others leaned in, One Nobel laureate reportedly whispered, "This might be the thing string theory's been waiting for." But how do you test a fifth force hidden behind a veil of gravity? That's where the pulses return. Again and again, Okoro's team began modeling the frequency spectrum of the Abel pulses under the influence of a fifth-dimensional scalar field. The result, a near-perfect harmonic alignment, something no current, four-dimensional model could explain. The pulses didn't decay like normal gravitational waves. They remained coherent, consistent, echoes not from collapsing stars, but from an interaction deeper than space-time itself. And then came a twist, when Okoro cross-referenced the Abel signals with data from a black hole in a completely different cluster max, J1149 plus 2223. She found similar rhythms, not identical, but harmonically related, as if two instruments were playing variations of the same song. Was it possible that black holes across the universe were responding to the same hidden force? That they were linked not just through gravity, but through something more fundamental, something like a cosmic metronome? If this fifth force exists, it doesn't simply act, it connects. Across space, maybe across time. And that raises a disturbing possibility. What if black holes aren't just the graveyards of stars, but the organs of some larger structure? What if they pulse, not randomly, but as part of a system, a mechanism we can't yet comprehend? That's not just physics. That's systems theory. It's biology. It's design. Are we willing to consider that? Are we ready to ask whether these pulses are not just echoes, but signals? And if they're signals, who or what is listening? Dr. Okoro doesn't claim to know the answer, but she's certain of one thing. Einstein's model was never meant to contain this. General relativity gave us the fabric of the cosmos, but these pulses, they come from between the threads, from whatever lies beneath the weave, and now, with every passing cycle, the black hole in Abel 2261 continues to beat. Regular, resonant, defiant, a message, a memory, or a force calling back through the noise. It's a haunting thought. Maybe we didn't discover the fifth force. Maybe it discovered us. By the fall of 2024, after months of scrutiny, one theory began to quietly dominate whispered conversations in gravitational physics forums, behind closed conference doors and in encrypted emails between research teams. The black hole in Abel 2261 might not be a black hole at all, or rather it might be more than one. The idea wasn't new, at least not entirely. Wormholes, bridges through space-time, have long haunted the pages of theoretical physics. First suggested in 1935 by Einstein and Rosen, these Einstein-Rosen bridges were once dismissed as exotic artifacts, mathematically possible, but physically implausible. They collapsed faster than light could cross them. They were fantasy. But the pulses from A2 to 6, 1b H1, were reawakening a forbidden hypothesis. What if a black hole was the mouth of a stable wormhole, not a portal for science fiction travelers, but a dynamic structure, anchoring to distant regions of the universe or to different universes entirely? And what if those pulses were feedback? Dr. Jian Yu, a gravitational lensing expert from Tsinghua University, was among the first to spot a strange anomaly in the light distortion around a 2261 BH1. Using updated lensing models and AI-enhanced telescopic data, she noticed the stars behind the black hole were bending light in ways that didn't fit standard black hole profiles, not once, not randomly, periodically, every 9.8 hours, same as the gravitational pulses the lensing patterns twisted, almost as if space itself were flexing. You described it as watching a shadow ripple across reality. This wasn't just gravitational. Lensing, it was temporal. Lensing as if time near the black hole was oscillating. But what could cause that? In classical relativity, nothing. Space-time curvature near a black hole should be smooth and continuous. But if this were a wormhole, things changed dramatically. Pressure from the throat, the narrow conduit connecting to universes, cause fluctuations that ripple outward. The pulse wouldn't come from the black hole swallowing matter, but from the wormhole stabilizing itself. Imagine holding a taut balloon underwater. It wants to collapse, but subtle adjustments keep it from imploding. Those adjustments might ripple through the water, or in this case, through space. Now imagine if something on the other side of the wormhole was interacting with it. This was the terrifying beauty of the theory. The black hole wasn't pulsing alone. It was echoing a dialogue. That possibility drew in a new player, CERN. The European Organization for Nuclear Research had quietly begun a project under its Beyond Standard Gravity division, using high-resolution magnetogravitic simulations to model the able 2261 pulses as wormhole dynamics. The simulations showed something haunting. Under very specific conditions, extreme mass, intergalactic emptiness, and quantum vacuum fluctuations, wormhole could stabilize. And once stable, it would breathe, expand, contract, pulse, exactly like what they were seeing. But this led to a darker possibility. What if the wormhole wasn't stabilizing? What if it was failing? If the pulses were signs of collapse, like the groans of a building before it crumbles, then we might be watching a cosmic warning play out in real time. A process Einstein himself once described as a rupture in the geometric continuity of space. If that rupture cascades, could it affect us? Directly, no. Able 2261 is 760 million light-years away. But indirectly, perhaps, the collapse of a wormhole, especially one connected to another universe, could unleash gravitational disturbances that ripple through the cosmic web. In the worst-case models, localized collapses could trigger topological shifts, microtears, in the fabric of space that might propagate. Small, rare, but not impossible. This theory sparked fierce debates. Most scientists still rejected the idea of traversable wormholes, citing a lack of exotic matter to stabilize them. But what if exotic matter wasn't needed? What if a fifth force, like Dr. Okoro suggested, was doing the work? Suddenly, all these wild ideas, solitons, fifth forces, quantum scars were starting to fit together like a puzzle. And that raised a chilling question. Few physicists even dared to speculate was something on the other side trying to communicate. Not aliens in the traditional sense, but perhaps physics itself, reacting to the strain. If wormholes connect regions of the multiverse, then feedback across them could be a kind of natural error correction reality attempting to rebalance. Or maybe we're reading too much into it. Maybe this is all just gravity's death rattle, an elegant dance of a structure that should never have existed in the first place. But even then, that raises another puzzle. If wormholes decay in microseconds, why is this one pulsing coherently for millions of years? Unless, of course, it was never natural. Unless something built it, an idea too radical for journals, but too compelling to ignore. And now, as more observatories tune their eyes toward A2 to 61BH1, the pulses continue, echoing, warning, or maybe welcoming. Long before the black hole in Able 2261 pulsed, before gravitational waves were ever detected, and before scientists dared to speak seriously of fifth forces or wormholes. There was one man who saw the cracks forming in our understanding. Ahead of the world, Stephen Hawking. For most, Hawking is remembered for the elegance of his popular science, his voice against cosmic silence. But to his peers, he was a radical man, willing to question the very foundations of reality. And in 1979, during a lecture at the Vatican, he hinted at something strange, something never fully explored. In a footnote, never published in fuller remark, read, "A black hole, under quantum geometric flux, may encode information in horizon surface vibrations. This effect, though imperceptible now, could one day be measurable. At the time, no one paid attention. There were no instruments, no way to test it. Horizon surface vibrations. It sounded like science fiction, but in light of the rhythmic pulses, observed from A2 to 6, 1BH. 1, it no longer feels that way. The idea that a black hole's event horizon could vibrate, subtly undulating in response to deeper forces, was considered heretical. The event horizon was thought to be a passive boundary, a mathematical point of no return, not a surface, not a participant, certainly not a communicator. But Hawking, obsessed with the information paradox, suspected otherwise. He believed black holes weren't the end of information, but the cloaking of it. The data, he claimed, was stored in subtle variations, in quantum perturbations on the horizon, a kind of holographic encoding, but without a framework or observational evidence. His equations sat in obscurity until now. In 2025, a postdoctoral researcher named Marisol Ibanez stumbled upon Hawking's handwritten notes in the Churchill Archives Centre in Cambridge. She had been digitizing rare transcripts for preservation when she found the margins of Lecture 7 covered in scribbled equations, strange symbols, and underlined terms like temporal echo, feedback, and surface perturbative storage. One expression stood out, delta I equals H. 2R, it wasn't elegant, but it hinted at information I being a function of a standing wave, psi squared on a curved horizon, R. A rough idea, but shockingly similar to the kinds of wave functions emerging from the Abel pulse simulations. Ibanez cross-referenced Hawking's sketches with new pulse data and saw eerie parallels. The frequency decay curves, the periodic amplitude modulation, they matched him perfectly. Yes, but enough to suggest that Hawking had anticipated this kind of behavior 40 years ago. The discovery triggered a flurry of activity. Teams from MIT, Max Planck, and ETH Zurich began reanalyzing Hawking's older black hole evaporation models through a new lens, one in which information wasn't lost but encoded at the very boundary. And this is where the concept of gravitational memory entered the picture. Gravitational memory is a theoretical effect where the passage of gravitational waves leaves a permanent displacement in space-time-like footprints pressed into fabric. Now, theorists began to wonder, could this memory be stored not just in space, but on the black hole's horizon itself? Could the pulses from A2 to 61BH1 be the result of memory retrieval, or worse, memory overload? The analogy is startling. Picture a vinyl record etched with sand. Now imagine that surface isn't physical, but a quantum horizon shifting in Planck-length ripples, encoding not music, but existence itself. Every particle, every photon, every collision swallowed by the black hole might leave a mark. If true, then black holes are not destroyers, but archives. And here's the twist Hawking never saw. If gravitational memory is real, and the event horizon encodes information via quantum vibrations, then perhaps it could also be read. What we're detecting in Able 2261 might not be a pulse. It might be a broadcast, but broadcast to whom? We stand at the edge of an epistemic chasm. If the information can be retrieved, it challenges the notion of irreversibility. It collapses the finality of death, at least in physics. And that opens doors we're not ready to walk through. Suddenly, the very idea of causality, of thermodynamic time arrows, begins to bend. Maybe entropy doesn't climb forever. Maybe black holes don't mark the end of knowledge, but its deepest form. So what was Hawking really onto? Not just equations, but philosophy. A view of the cosmos in which information, pure, undying information, is the true currency of reality. Hawking died in 2018. He never saw gravitational waves, never saw the black hole shadow in M87, never heard the pulse, but in his silence, he may have already known. He once said, "The universe doesn't allow perfection, but it does allow explanation." And perhaps, within the pulse of a 2261 BH1, that explanation is beginning to whisper back. A rhythm, a memory, a lost equation, finally found. On the morning of April 3rd, 2025, a junior data analyst at the LIGO Hanford Observatory noticed a spike so faint, it barely rose above the system's noise threshold. It lasted less than a second. A fluctuation in the gravitational wave field, far below the strength of a typical black hole merger. No chirp, no crescendo, just a soft, symmetrical anomaly, and it wasn't alone. Similar signatures had quietly appeared at LIGO's sister site in Livingston, and at the Virgo detector in Italy, all from the same region, the distant heart of the Able 2261 cluster. The anomaly didn't match anything catalogued in the growing library of black hole collisions. It lacked the sharp waveform of a neutron star crash or the fast decay of a stellar mass death spiral. Instead, it was rhythmically spaced, harmonic, a gravitational signal with intervals that mirrored the X-ray pulses observed from A2 to 6, 1BH, one every 9.8 hours. When overlaid on each other, gravitational, electromagnetic, and radio eerie picture emerged, an interference pattern in classical physics. Interference patterns are created when waves overlap, constructive and destructive interference, painting fringes of intensity, like the ripple patterns seen when two stones are dropped into a pond. But this wasn't water. It was spacetime itself. The gravitational waves, tiny as they were, suggested a standing wave, structure oscillations caught between boundaries. That alone was perplexing. Standing waves in gravity, that implied reflection. But what could possibly reflect gravitational waves? In black hole physics, the event horizon is the point of no return, an absorber, not a mirror, unless something deeper lies beneath. Dr. Farida Undur, a gravitational theorist from Senegal's Institut Pasteur, proposed something radical. The standing waves weren't being reflected by the black hole itself, but by the geometry of the surrounding. Space curved and compacted into a quasi-resonant cavity. According to her model, certain ultramassive black holes could develop metastable gravitational cavities just outside the event horizon. Picture a spherical chamber where the shape of space traps and bounces gravitational energy like a cosmic echo chamber. Under normal conditions, this cavity would collapse quickly, but if energized by an external field, like the hypothesized fifth force, it might sustain. And then came the bombshell, when Endor ran the math through her modified tensor models. She found something shocking. The waveform pattern matched a class of solutions called quasi-normal modes, theoretical predictions for how spacetime rings after being disturbed. But these were not decaying. They weren't echoes from a past event. They were persistent. That shouldn't be possible, if true. This meant a 2 to 6 1BH1 was not just warping spacetime, it was holding it in tension, like a plucked string that never stops vibrating. The interference pattern was not a side effect. It was the signature of a system in balance. The implications were immediate and staggering. A black hole locked in resonant gravitational tension suggests internal structure, not necessarily a solid core, but a framework layers or shells of spacetime interacting in ways general relativity never predicted. Perhaps even dimensional membranes. The theory struck at the core of what we thought a black hole was. If waves could persist in this way, if the event horizon wasn't a perfect absorber, then what else could escape? Not particles, no, but information. In other words, the interference pattern may not just be the sound of gravity. It could be the language of memory. Dr. Endar wasn't alone in thinking this way. At CERN, experimental teams began collating gravitational and electromagnetic data into a cross-spectrum analysis. They found phase-coherent spike signal alignments that suggested not just a shared origin, but coordinated behavior. Imagine that, light and gravity dancing together in locked rhythm across millions of years of distance. One researcher likened it to the universe playing chords. Others weren't so poetic. To them, the standing waves pointed toward instability. If energy couldn't radiate out, it might collapse in a feedback loop, a gravitational resonance cascade, the cosmic equivalent of glass shattering from its own vibration. It raised the stakes. If a 2 to 6 1BH one was sustaining these waves, then it wasn't static, it was evolving. And if it broke symmetry, if the resonance collapsed, it could tear open new geometry's pockets of twisted spacetime, with consequences no one could predict. There was also the unsettling question of pattern recognition. Some researchers began using neural nets to translate the interference signal into visual maps. What they found were recursive patterns, nested inside oscillations. Some formed spirals, others Fibonacci-like geometries. One even mapped out what looked eerily like a Mobius looper, one-sided surface in which time might fold back on itself. This wasn't just a random wave. It was organized, so we're left with a choice. Do we interpret this as evidence of deeper physics, a bridge between gravity and quantum mechanics? Or do we consider something more speculative, that we're witnessing an emergent phenomenon, a form of self-structured information encoded in gravitational fields? If so, then a 2261b H1 isn't just bending space, it's thinking, or, at the very least, remembering. It began, oddly enough, in a basement lab in Helsinki in deep space in 2024. A team of low-temperature physicists at Aalto University was studying analog black holes, fluid systems that mimic the behavior of actual black holes using superfluid helium. Their goal was simple: simulate event horizons in a controllable, observable environment. No lasers, no exotic matter, just carefully chilled atoms behaving like quantum whispers. What they discovered changed everything. As waves moved through, the superfluid researchers observed distinct, localized pattern ripples that persisted even after the system stabilized. These weren't just noise. They formed structured interference, like the memory of an event burned into the field. They called them quantum scars. In quantum chaos theory, a scar is a strange phenomenon patterns left behind in quantum systems that should be completely random. They're echoes of classical behavior etched into the probabilistic fog of quantum mechanics. A kind of cosmic muscle memory. When Dr. Leena Koskinen published her results, no one outside the analog physics community paid much attention. That is, until someone overlaid the Alto team's scar pattern on the pulse frequency map of the black hole in Able 2-61. It matched. Not perfectly, but close enough to send chills down the spine of anyone who understood the implications. What if the black hole's interference pattern was a macroscopic quantum scar? In essence, what if a 2261BH1 wasn't just vibrating, but remembering? This idea began to take root across theoretical physics departments. Normally, black holes are thought to erase their past. No information about what falls in can be recovered, not the shape, structure, or arrangement, just mass, spin, and charge. That's the essence of the no-hair theorem. But scars challenge that. Scars suggest that memory can outlive entropy, that even in chaotic, highly curved systems, echoes of past structure remain, ghosts of what once was. If this could happen in a fluid chamber on Earth, why not in the fabric of space-time itself? Dr. Koskinen was flown to CERN to present her findings. There, particle physicists and gravitational theorists watched with growing awe as she laid out the similarities between subatomic superfluid fields and the warping patterns observed around 2261-BH1. The connections deepened when researchers found recursive harmonics in the black hole's pulsar layering of signals that couldn't be explained by classical models. It was as if each new wave carried a faint trace of the one before, subtly evolving, like a memory loop. Now imagine that, a black hole that accumulates its own past pulses, building resonance layer upon layer, each echo reinforcing the last. Not in a literal brain, but in the language of quantum structure, could a black hole possess temporal architecture? Not consciousness, not intention, but a memory scaffold, where certain configurations leave lasting impressions on the field. Like handprints in wet cement. It reframes everything. What if a 2261BH1 is not simply a remnant of gravitational collapse, but a record of events that once happened, a cosmic black box, not just holding data, but embodying it? Some researchers, cautiously, began calling it the librarian. The scar patterns weren't random, they hinted at encoded information. Sequences that might, with the right mathematical lens, reveal prior interactions, mergers, infalls, even quantum fluctuations from the earliest moments after the Big Bang. If that's true, then each black hole could be a page in the universe's autobiography, and this one, it may be the first chapter we can read. Naturally, skepticism surged. Detractors argued that drawing parallels between tabletop physics and celestial titans was irresponsible. Superfluid analogues are not black holes, but the patterns wouldn't go away. They reappeared in more simulations, more reconstructions. The idea gained weight not as evidence of consciousness, but as evidence of coherence. The implications ripple outward. If memory can persist in gravitational systems, then time itself may not be what we thought. Perhaps the arrow of time, ever forward march of cause to effect, isn't a one-way street. Maybe it's a spiral, a helix, where moments loop, intersect, and leave traces. And if that's true, can memory become signal? Can scars become communication? One physicist put it this way: if gravity can remember, maybe it can speak. That question has haunted the A2261 research group ever since. What began as pulses has become pattern. What was once noise is now structure. But is it intentional? Or is it simply the universe folding back on itself, leaving fingerprints as it turns? Ask yourself this: if you found a pattern in the static of the universe, echoing across dimensions of space and time, would you decode it, or would you fear what it might reveal? The scar remains. The black hole pulses. The librarian remembers. If the universe is a stage, then black holes are its most enigmatic actors, silent, veiled, inscrutable. For decades, Einstein's script has guided their performance. Space bends, time slows, gravity reigns. But as the curtain rises on the 21st century's most haunting puzzle, a new contender steps into the limelight, a principle so audacious it rewrites the very concept of reality itself: the holographic principle. This idea, first whispered in the 1990s by Gerard T. Hooft and then by Leonard Susskind, is as strange as it is seductive. What if our three-dimensional universe is really a projection? What if all the information that describes our world is encoded not in the volume of space, but on its surface, like patterns etched on the face of a coin? In this vision, black holes are not exceptions. They are the rule's ultimate test. Einstein's general relativity treats the event horizon as a boundary, a veil beyond which information vanishes forever. But the holographic principle insists otherwise. Nothing is lost. Every quantum, every flicker of matter or light is recorded on a two-dimensional cosmic screen at the very edge. A universe as a hologram. Dr. Satoshi Watanabe, a theoretical physicist at Kyoto University, has spent years at the intersection of relativity and information theory. His group, watching the mysterious pulses from A2 to 61BH1, realized that the black hole was not breaking physics, was revealing deeper consistency. The rhythmic echoes were not anomalies. They were data encoded in the horizon's very structure. It was as if the black hole was running a cosmic program, each pulse a line of code, each resonance a subroutine. When Watanabe and his colleagues mapped the frequencies against models of holographic entropy, the informational content of a surface, areas they found correlations too sharp to ignore. The pulse intervals weren't random. They matched predicted jumps in surface entropy. What does this mean? Imagine a vault so secure that every change on its surface is a record of everything that's ever gone inside. Now imagine that the vault is the edge of a black hole and the data isn't just there, but forms the very substance of reality. This is the holographic principle in action. It also means that Einstein's story, the story of black holes as featureless endpoints, may be incomplete. Not wrong, but limited. The pulses, the interference patterns, the scars, all of it is the surface writing the story of the inside. For Watanabe, the implications are profound. If the universe truly works this way, then black holes are not only archives, they are interfaces, connectors between our reality and the ultimate code from which all things arise. His group went further. Using quantum information theory, they suggested that the persistent pulses might be evidence of error correction in the cosmic code. Like a computer safeguarding its memory, the black hole could be constantly checking and restoring the information on its horizon. Every pulsar checksum, every harmonica correction. If so, then a 2 to 61BH1 is not just a grave, It is an active participant in the universe's computation. Its pulses may be the echoes of this processor, kind of cosmic debugging, but there is a philosophical cost. If the holographic principle is true, then we ourselves, our memories, our dreams, our struggles might all be part of this projection. Not less real, but differently real. Not souls in a shell, but patterns on the edge. This realization sent a shiver through the scientific community. Is identity itself a shadow? Is reality a mask worn by information? It's a question as old as Plato and as modern as quantum computing. And yet, the evidence from A2 to 6 1BH1 cannot be denied. The pulses fit. The horizon encodes. Einstein's vision stands majestic and beautiful, but behind the veil. The holographic script is being written in real time. There are critics, of course, those who argue that this is philosophy, not physics, that without direct observation, the holographic principle remains a tantalizing metaphor. But the data grows. The patterns multiply. Each new observation hints at the same unthinkable conclusion. Black holes are not just cosmic garbage disposals, they are the gateways to a deeper encoded order. If this is true, then the pulses from A2 to 6, 1BH1 are more than a scientific curiosity. They are the voice of the universe's operating system, a message written on the edge. So, what would you do if you could read that message? Would you dare to decode the cosmos itself? As the black hole pulses steadily, inevitably the universe's secrets ripple across the holographic screen. And for the first time, we might finally be ready to see what lies behind it. The shadow of a black hole is not simply a region of darkness. It is the most enigmatic silhouette in the cosmos. It's where light itself surrenders, caught in an endless dance around the event horizon before vanishing forever. In 2019, the Event Horizon Telescope gave humanity its first glimpse of such a shadowy, ghostly ring around the black hole in M87, imprinted onto the canvas of spacetime. For most, it was proof of Einstein's predictions. But for a new generation of researchers, shadows became a stage for subtle, invisible drama. When astronomers pointed the EHT at Abell 2261, the stakes were higher. What would the shadow of a pulsing, rule-breaking black hole reveal? Initial images suggested the expected: a dim core surrounded by a lopsided ring, warped by gravitational lensing. But as more data poured in, a pattern emerged that no one had anticipated. The shadow flickered, not wildly, not like a candle in a storm, but gently, rhythmically, its brightness waxing and waning with uncanny regularity. This wasn't noise from the telescope array or a byproduct of calibration. The fluctuations tracked the black hole's mysterious pulse, cycling in perfect synchrony every 9.8 hours. It was as if the event horizon itself was breathing. Dr. Tara Guillory, an astrophysicist with the EHT collaboration, watched the data unfold. In disbelief, "We've never seen a black hole's shadow do this," she explained. "It's like watching the surface of a pond ripple when you can't see the stone." Guillory and her team ran the numbers again and again, accounting for every possible source of aeromispheric effects, instrumental drift, cosmic dust. Nothing explained it. Attention turned to the black hole's environment. Could orbiting matter be casting variable shadows? Could magnetic turbulence be responsible? Yet, the region around A2261BH1 was eerily empty, a stark contrast to most active galactic nuclei. There was nothing visible to create the rhythmic change. The answer, it seemed, was not in what surrounded the black hole, but in the horizon itself. Theorists raced to model what could make an event horizon flicker. In classical general relativity, the event horizon is an immutable, boundary-unchanging absolute. But if the horizon is not a passive line but a dynamic membrane, as some quantum gravity models suggest, then it might respond to deeper forces. Consider a drum skin still and taut until struck by a rhythm only the player can hear. In this analogy, the black hole pulses act as the drummer, and the horizon becomes a resonating surface, flickering in response. Some physicists invoked the holographic principle once again. If all information is stored on the horizon, then any process that modulates this information error correction, memory retrieval, even quantum scars might manifest as changes in the shadow's brightness. The event horizon is not just a point of no return, but a living interface between the known and the unknowable. This led to radical speculation. If the shadow flickers, could we be witnessing quantum fluctuations on a cosmic scale? Was the horizon's brightness the sum of countless micro-interactions, each one an encoded bit of the black hole's memory? Others dared to go further. Could the flickers be messages, signals broadcast across the void? Could the black hole be using its shadow to speak, each modulation a word in an ancient gravitational language? The idea found its most poetic voice in Dr. Guillory herself. If a black hole could dream, its shadow would be the dream's reflection. But for all the lyricism, the reality was sobering. If the event horizon is fluid, if it truly moves and shifts, then what lies beyond may be more than an abyss. It may be a dimensional veil, rippling in response to forces we are only just beginning to understand. A place where the old boundaries of time and space blur, and new physics beckons. The shadow flickers, and with each pulse, the cosmos hints at secrets just out of reach. What would you do, standing on the shore of such a mystery, watching the horizon ripple in silent song? Would you listen for meaning? Or would you fear what the next flicker might reveal? One thing is certain: the darkness at the heart of Abel 2261 is not as silent as we once believed. It flickers, it breathes, it waits. In the realm of cosmic speculation, there exists a question that blurs the line between science and myth. What if there is another world, a mirror universe hiding in plain sight? For decades, the concept of mirror matter lingered on the outskirts of physics. It was the ghost in the equations, the shadow partner to every known particle. Invisible, undetectable by ordinary means, but possibly more real than we dare to believe. Now, with the pulses and flickers from a 20 to 61 BH1 breaking the rules of known physics, mirror matter is no longer a fringe idea. It's a lead suspect. Dr. Simone Kregsi, an experimentalist at CERN, became obsessed with the anomaly. She'd spent years searching for deviations in the behavior of fundamental particles, hoping to find evidence of something that didn't quite belong, something that hinted at a twin world. Kregsi's team began to wonder, could the black hole's strange signals be the result of interactions with mirror matter? Could the fifth force proposed by Dr. Okoro be a portal not just to another dimension, but to an entire mirror cosmos? The more Kregsi's group investigated, the more compelling the hypothesis became. In laboratory experiments with ultra-cold neutrons, faint anomalies appeared. The neutrons sometimes vanished and reappeared, sometimes with energies ever so slightly altered, as if they'd spent a fraction of a second somewhere else. Could black holes be more than gravitational traps? Could they act as gateways, not just two unknown places in our universe, but to this hypothesized mirror realm. If so, the implications are staggering. For every atom in our universe, there could be a twin unseen reflection, bound to ours through subtle, ghostly fields. Under normal circumstances, these fields would be silent. But in the heart of a black hole, where densities and energies reach unimaginable extremes, they might become loud. Dr. Krejci called these connections ghost fields domains, where ordinary and mirror matter brush against each other, transferring information or energy. If the black hole pulses were modulated by these ghost fields, it might explain why the signals didn't decay like ordinary gravitational waves. Instead, they lingered, reinforced by feedback from the mirror universe. What if the black hole's rhythmic heartbeat was, in fact, a handshaker coupling between two realities? Further intrigue emerged from the Large Hadron Collider's most recent runs. Their strange blips appeared in particle trajectories, soon accounted for losses of energy and momentum that couldn't be explained by known physics. Most were dismissed as noise, but Krejci's team saw a pattern. The timing of these blips sometimes matched the pulse cycle observed in a 2261 BH1, down to the hour. It was as if, at regular intervals, energy flickered from our world to somewhere else. Skeptics urged caution. Quantum experiments are notoriously sensitive, and pattern-seeking can lead scientists astray. But as more data arrived from gravitational observatories and high-energy particle labs, the coincidences mounted. A new idea crystallized. Perhaps the black hole was not just a place where information accumulates, but a junction, a node in a cosmic web where realities converge and diverge. If true, then black holes may be the only places where mirror matter becomes temporarily tangible, where the veil thins and two universes become one, if only for the briefest of instants. But what does it mean for us? If reality is doubled, if every law of nature has a mirror twin, what does it say about identity, about fate, about the singularity of consciousness? In the closing days of 2025, Dr. Krejci stood before an audience of physicists in Geneva, her hands trembling slightly as she presented her team's findings. Perhaps, she said, the universe is not alone. Perhaps it pulses with the rhythm of a ghostly partner, hidden in the same darkness as our own fears and our greatest hopes. So the next time the black hole's pulse sweeps across the sky, ask yourself, is it a drumbeat from the void, or a signal from the other side of the cosmic mirror? Would you reach through if you could? Or is it enough to know that in the darkness we are not alone? The echoes linger, the fields entwine, and somewhere in the ghostly reflection, the pulse beats on. In the world of big science, not every discovery is made in a billion-dollar laboratory. Sometimes, the future of physics lies buried in the dust of forgotten notebooks, in datasets collected by hands that never knew what they held. The story of a 2 to 6 1BH1's pulse isn't just about the present. It's also about a faint signal from the past, a mystery that began not in a shining metropolis, but in a frozen bunker beneath Siberian permafrost. The year was 1986. The Cold War was nearing its end, and the Soviet Union's Institute for Cosmic Research had fallen on hard times. But in a windowless basement, a team of physicists led by Dr. Leonid Boronev were trying to detect gravitational anomalies using a home-built torsion balance. They were looking for evidence of seismic disturbances, military, not cosmic, but what they recorded was something no one could explain. Among thousands of lines of handwritten readings, one data trace stood out: a rhythmic, low-frequency fluctuation. spaced with uncanny regularity every 9.8 hours for nearly 3 days straight. The team marked it as unexplained and moved on. The Soviet Union was fracturing. The world had other things to worry about. The data sat, ignored, for decades. The notebooks gathered dust. Dr. Baronev retired and eventually passed away, never realizing that he had glimpsed the same cosmic drumbeat that would one day echo through the world's most sophisticated telescopes in 2025, as the A2261BH1 anomaly made headlines. A young researcher named Vera Krupin stumbled upon Baronev's files while digitizing the Institute's archives. The moment she saw the repeating intervals, her heart pounded. She cross-referenced the date and time with records of known cosmic and terrestrial events. Thing-matched could it be? Had a team in 1986 detected the very same pulse, decades before anyone knew what it was? Krupin reached out to international collaborators, and soon the world's physicists were poring over the faded ink of a bygone era. Analysis confirmed it. The frequency, the waveform, even the amplitude were eerily similar to the gravitational pulse from A2261BH1. But how was this possible? The Siberian apparatus was crude by today's standards. Its sensitivity shouldn't have allowed it to detect signals from 760 million light-years away, unless the pulse was stronger then. Or perhaps, in moments of cosmic alignment, the Earth itself acts as a giant antenna, amplifying signals that normally fade into the void. This idea sparked a new wave of curiosity. If the A2261BH1 pulse had been visible in the 1980s, how many other unexplained readings were hidden in the archives of old observatories? How many errors in the margins of science were actually fragments of the same universal pattern? A global effort began. Physicists from China, the US, and Germany scoured past records, uncovering similar blips in 1997 in South Africa, in 2008 in the Chilean Andes, even a whisper in an Australian seismic lab in 2012, each a thread in a tapestry that no one had thought to weave. The realization was profound. The universe had been whispering for years. We simply hadn't learned how to listen. The moment became a reckoning for the scientific community. How much knowledge is lost to skepticism? How many truths are dismissed as noise, anomalies, or mistakes? Vera Krupin, presenting her findings at a conference in Geneva, put it plainly: maybe the greatest barrier to discovery isn't technology, but imagination. We have to be willing to see the impossible hiding in plain sight. There is a human lesson in this. Science is not just the march of progress. It is the willingness to revisit the forgotten, to see old mistakes as potential windows to new worlds. Baranev's experiment, once deemed irrelevant, became a key to the greatest cosmic puzzle of our era, and the pulse continues. Now, every new detection, every time the beat rolls across the planet, scientists and dreamers alike wonder how many more signals are still lost in the dust of time. What else have we overlooked? The cosmos does not shout its secrets. It whispers them, quietly, insistently, to anyone patient enough to listen. So next time you hear of a scientific anomaly, something discarded, unexplained, ask yourself, what? If that was the first sign of a revolution, what other signals, buried in forgotten notebooks or flickering on old magnetic tapes, might be waiting to be found? The experiment no one noticed has become the discovery the world cannot ignore, and, in the faint echoes of the past, the future pulses of her onward. In the feverish days following the rediscovery of the Siberian experiment, the conversation surrounding A2261BH1 began to spill out of the realm of hard science and into the tangled wilderness of philosophy, as physicists mapped the black holes. Memory, philosophers saw something more profound, an object that shattered not just equations, but our deepest assumptions about reality itself. If a black hole can remember, what is it, truly? Is it a thing, a place, a process, or is it a story that time itself struggles to contain? Dr. Alina Barlow, a philosopher of science at Oxford, found herself at the epicenter of this debate. She convened roundtables with physicists, information theorists, and mathematicians, asking a question that echoed through centuries. What is the nature of the self, if memory can outlive matter? If the pulses from A2261BH1 are echoes of ancient information, then the black hole isn't merely a cosmic tomits, a living record. Barlow drew from the musings of ancient Greek thinkers, who believed the cosmos itself had a solar memory etched into the turning of the spheres. Now, in the age of quantum mechanics and gravitational anomalies, the soul of the cosmos appeared in the flicker of a black hole's shadow, the drumbeat of a pulse traversing space and time. The conversation grew stranger still when theorists proposed that black holes, if able to encode and release information, might possess something like a conscious filter, a capacity to select, distill, and transmit data. Not consciousness as we know it, but an emergent property born from the entanglement of energy and memory. Is the black hole aware? A student once asked at Barlow's seminar. Not in any way we'd recognize, she replied, but perhaps it's the universe contemplating itself, a node of reflection at the edge of reality. This speculation, once the territory of science fiction, now rippled through the highest halls of scientific discourse. Conferences buzzed with talk of informational agency, causal boundaries, and cosmic observers. Some rejected the notion as poetic excess, clinging to the comfort of cold equations. But others, intoxicated by the new evidence, wondered if reality itself was stranger, more relational than we'd ever dared believe. If black holes are not erasers of information but archives, if they filter and encode the history of everything they consume, then every black hole is a philosopher in the cosmic web, holding questions we have yet to learn how to ask. This idea resonated beyond the academy. Artists, theologians, and writers began to see in the black hole a new metaphor for identity, loss, and hope. Novels and poems emerged, capturing the existential awe of a universe that refuses to forget. In galleries and films, the shadow of A2261BH1 became a symbol for memory surviving oblivion, a reminder that even in darkness, meaning endures. But the debate was not without unease. If information is preserved, does it mean everything is ultimately knowable? Or does the black hole's pulse conceal as much as it reveals? Is memory itself reliable, or merely a fragmented echo of an unknowable whole? Dr. Barlow challenged her colleagues with another question. If black holes are records, who or what is the reader? Is it us, deciphering patterns from across the void? Or is it the universe itself, seeking coherence through these mysterious pulses? As data from A2 to 61BH1 continued to accumulate, the line between observer and observed grew thin. The act of measuring the pulse became an act of co-creation, an entanglement of mind and cosmos. The black hole did not simply exist, interacted, responded, changed in the telling, and if that's true, the implications reach far beyond astrophysics. Maybe the universe is not a collection of separate things, but a tapestry of relations. Black hole are not where the threads of space, time, and information are woven tightly together. In this view, meaning and memory are not byproducts, but the very substance of reality. As the chapter closed on another international symposium, physicists, philosophers, and poets alike, standing under the cold light of distant stars, Dr. Barlow spoke once more. "We used to think black holes were the end," she said. "Now, I wonder if they're beginnings, the universe asking itself, again and again, what it means to exist, to remember, to be known. The debate is not settled. It may never be. But in the deep silence of space, the pulse continues, an invitation to question, to wonder, and to find ourselves reflected in the darkness. Would you dare ask the black hole what it remembers about you? Would you believe the answer? Or are we all, in the end, philosophers at the event horizon, gazing into the dark, searching for the story of ourselves? In a sunlit room lined with humming supercomputers at the European Space Operations Center, Dr. Marcellus Tsai prepared to launch a new round of simulations. For months, the best minds in theoretical physics and computational science had struggled to reconcile the tidal waves of data pouring in from A2 to 6, 1BH, 1 pulses, flickers, scars, and the mysterious shadow. But the raw mathematics kept hinting at something even stranger than a misbehaving black hole. The rules of reality themselves might be shifting. Dr. Tsai's team decided to build a virtual universe, seeded with every pulse and parameter from the Abel cluster anomaly. The goal: see what happens when you let the cosmos run, governed not by Einstein's equations alone, but by the new, pulse-infused rules emerging from the black hole's behavior. This wasn't just data crunching. It was an act of cosmic reimagining. The simulation began in silence, a digital birth of space and time. But as the virtual black hole awoke, its regular pulse rippled outward. Instead of dampening, the echoes grew. Space-time, normally smooth and continuous, began to fracture and branch. Tsai and his team watched, mesmerized, as their digital universe split. One echo would pass through a region, and suddenly, two parallel geometries would blossom where there had been only one. Timelines bifurcated like the veins of a leaf. Galaxies appeared, vanished, and then appeared again, fractals within fractals, all orchestrated by the rhythm set at the simulation's heart. It was as if the black hole's pulse was a cosmic metronome, dictating the moments when the universe could choose its path, forks in the fabric of reality. For every pulse, a possible cosmos. For every echo, a new world. The implications were staggering. Could this be evidence for the multiverse, not just a collection of parallel worlds, but a living, branching tree, each limb shaped by the memory and rhythm of ancient black holes? Could it explain the paradoxes of quantum mechanics? The uncanny way particles seem to exist in superpositions, both here and elsewhere at once. As Tsai's simulation ran, he noted a chilling pattern. Every time the black hole's pulse was allowed to alter the laws of gravity, the universe grew stranger. Constants drifted. The speed of light, the strength of forces, values we take for granted, began to wander, branching with each cosmic beat. It was as though the cosmos was not fixed, but computing itself forward, rewriting its own code at every crossroads. Dr. Tsai likened it to a cosmic blockchain, an indelible ledger. Each pulse a new block, each echo a record of past choices. In some universes, the black hole faded quietly. In others, it exploded, birthing new realms. Occasionally, the simulation would crash altogether, a digital analog for cosmic collapse. For the physicists watching, this wasn't just entertainment. It was a warning and a revelation. Our own universe, it seemed, might be just one thread in a far greater tapestry, one whose pattern is forever shaped by the memory and pulse of its most mysterious denizens. The results were shared at the World Science Festival in New York. Audiences watched in awe as visualizations unfolded, universes blooming and dissolving to the rhythm of an invisible drum. For some, it was beautiful. For others, terrifying. If reality is truly so fluid, so prone to fracture and recombination, what hope is there for meaning, for permanence? Yet, amid the uncertainty, hope persisted. The very act of simulating a fractured cosmos, of seeking order within chaos, was itself a gesture of faith, a belief that understanding is possible even in a universe of infinite possibility. Psi closed his presentation with a question to the world. If the cosmos computes itself, who writes the code? Is there a pattern beneath the pulse? Or are we all part of an endless branching, every choice, every life, every universe, a note in a symphony without end? As the simulation powered down, the echoes of a 2261 BH1 remained. The boundaries between reality and imagination blurred. And for those who dared to look deeper, the message was clear. Nothing is fixed. Everything branches. The black hole does not just remember, it creates. And so, the fractured cosmos pulses on. Would you choose to see every possible world? Or is this flicker of consciousness in the vast, branching dark enough? By late 2025, a palpable sense of anticipation hung in the air across the world's great centers of scientific thought. The rules that once governed our understanding of black holes and, by extension, the universe were bending, if not breaking. Old equations no longer fit. Data from A2 to 6 1BH1, once an isolated curiosity, now glimmered as the herald of a new law of nature. The search was on for something that could contain Einstein, quantum mechanics, the holographic principle, and the pulse all in one breathtaking vision. It was in this spirit that a coalition of researchers, led by Dr. Akira Lermontov at the Max Planck Institute, unveiled what they called relational gravity. It wasn't a replacement for Einstein, but an expansion, a deeper framework built on the very foundation of connections. Relational gravity held that gravity was not just a curve in the fabric of spacetime, but a manifestation of the relationships between all bits of information, mass, energy, memory woven throughout the cosmos. In this model, black holes were no longer dead ends. They were hubs, intersections of space, time, and information, humming with pulses that preserved and transmitted the memory of cosmic events. The equations were mind-bending but elegant. Space-time itself became dynamic, shaped not just by mass, but by the history and entanglement of everything within it. A black hole's pulse was no longer an anomaly, but the signature of this deeper order, a message encoded in the rhythm of the universe. For months, debate raged. Could relational gravity explain the persistent interference patterns, the flickering shadows, the echoes and scars? Again and again, the new theory passed test after test. Where general relativity broke down at the singularity, relational gravity offered smooth, finite descriptions. Where quantum mechanics predicted paradox, the new model delivered a tapestry of intertwined realities, consistent with the holographic script. But perhaps most astonishingly, The equations suggested possibility technologies and phenomena once dismissed as fiction. If black holes are information hubs, could we one day retrieve their archives, decode the memory of stars, even universes long vanished? Could gravitational pulses be used as messages, or even bridge as corridors through time or between worlds? Speculation soared. Some groups modeled theoretical gravitational engineering, using controlled pulses to stabilize wormholes or send signals across the cosmos. The wildest visions proposed universe building itself, civilization advanced enough to shape the very laws of physics with each beat of a cosmic drum. Yet, amid the dreams, caution reigned. With each new insight, the universe grew both more wondrous and more daunting. If relational gravity was true, we stood at the threshold of powers and mysteries that could lift us or destroy us. Dr. Lermontov's team found themselves haunted by philosophical questions. Does the universe have an end, or only endless recursion cycles of memory, branching, recombination? Is the future something we discover, or something we help to write? In a memorable moment during a global symposium, a young physicist asked, "If we can shape the pulse, do we have a responsibility for what comes next?" Lermontov smiled, acknowledging the weight of that question. "The universe is not a fixed machine," he answered. "It's a living network. Every connection, every memory, every pulse matters. So where does this leave us?" With relational gravity, Einstein's legacy is not overthrown, but embraced his frame of space and time, now woven into a vaster, more intricate fabric. The old dream of a theory of everything is replaced by something richer, a theory of relation in which every fact, every particle, every story is inseparable from the rest. At the heart of it all, the black hole in Abel 2261 pulses and a beacon, a warning, an invitation. What will we do with the last law? Will we dare to remember what the universe itself has not forgotten? Or, in the silence between pulses, will we discover the greatest secret of all, that we are not only observers of reality, but its co-authors writing the next verse in the endless cosmic song? The future waits. The black hole pulses, and the last law is only the beginning. By the close of 2025, the world had changed, not with a bang, but with a pulse. From observatories to living rooms, from supercomputer arrays to late-night podcasts, everyone was asking the same question: what does it mean when the rules we trusted for a century are suddenly, gloriously uncertain? Scientists no longer spoke of black holes as mere engines of destruction or even as cosmic archivists. They became something new: messengers, keepers of memory, architects of possibility. The pulse of a 2261 BH1 had transformed not just the story of black holes, but the story of us. For the first time in living memory, humanity looked into the darkness and saw not emptiness, but a living pattern order in the chaos, invitation in the mystery. The debates raged on. Some physicists clung to the elegance of Einstein's equations, unwilling to surrender the beauty of certainty. Others dove headlong into the new mathematics of relational gravity, mapping networks of meaning, tracing the ways every connection echoes across the universe. Old paradigms dissolved, new ones crystallized. The edge between science and philosophy blurred, and the boundary between what is known and what is possible seemed to flicker, just like the shadow of a black hole. But perhaps the greatest change was not in the equations or the theories, but in the hearts and minds of those who watched the story unfold. People everywhere began to wonder if a black hole can pulse. Remember, and communicate what else might the universe be trying to say. What secrets are woven into the cosmic background, just waiting for us to notice? And what will we do now that we know even the darkness can sing? In classrooms, children traced the echo of the pulse across model universes, their imaginations racing ahead of the data. In coffee shops, friends argued about time, memory, and whether our world was just one leaf on a fractal tree of realities. And in quiet moments beneath the stars, some simply listened, feeling, perhaps for the first time, that they were part of a story far older and deeper than they had ever believed. What comes after certainty is not despair. It is wonder, it is humility before the immensity of what we do not yet know. It is the courage to keep asking questions, even when the answers shatter what came before. The universe has never promised us certainty, only the invitation to explore, to imagine, to revise. Science, at its best, is not the fortress of knowledge, but the ongoing act of curiosity, endless conversation between what is and what could be. And so, the black hole pulses on its rhythm. A question, its shadow, a promise, its memory, a challenge to everything we thought was true. What comes after certainty? You do, we do. The next generation of dreamers, builders, listeners, and storytellers, ready to take up the search, to chase the pulse, to hear the universe's next secret. Because, in the darkness, we are never alone, and as long as we dare to listen, there will always be a new horizon flickering, calling, waiting for us to reach it.